Assalamu alaikum students and welcome to another lecture of Slate. This is Sir Khawaja Yasin. Let's study chemistry. In the last lecture of the first chapter of AS chemistry, we were talking about the electronic configuration, which was unlike the O levels, obviously more enhanced ones. We talked about the shells, we talked about the subshells and the number of electrons that one subshell can have, and the shapes obviously. And then we further wrote and drew the electronic configuration along with the orbitals of first 10 elements. Now, when we came to sodium, obviously, we saw the electronic configuration where it started off with 1s2, 2s2, 2p6, and now we jumped off onto the third shell, hence 3s2. This will go on for a long time because if we keep on adding these shells, what is going to happen? For instance, after sodium, we have magnesium. So 1s2, 2s2, 2p6, and 3s2. And obviously after 3s2, we are going to jump towards, for aluminum, we will jump towards 1s2, 2s2, 2p6, 3s2, and then 3p6. This will go on. We will keep on adding orbitals, electrons in orbitals. And remember, all these orbitals are degenerate. They have the same energy. We will fill them. In what way? That if P has 2 electrons, the second electron will not come here. It will come in the next P orbital because they all have the same energy. If I fill this one first, that would mean the px or the first P orbital is lower in energy because electrons fill the lower energy orbitals first. So this is the concept we've already dealt with. So if we start making the electronic configuration of first 20, we've made 13. Let me share the file where we can see how do they all look for other elements. Now that is the electronic configuration of the next elements. Sodium, magnesium, aluminum, silicon, phosphorus, so on and so forth. But look what happened after argon. 3p6, it's complete. We were supposed to have a 3d orbital. Because remember we studied that how there is a d orbital in third shell as well, third principal quantum, third energy level as well. But that's not how electrons work. The electron filling is a different matter. In order to fill the electrons, what do we do? Because if you note, for 3p for potassium, there is a 4s. No, not a 3d. There is no 3d here. It is a 4s. Same is the case here. So what is happening? Because the rule is electrons fill in the lower energy orbitals first. And if electrons are being filled in 4s before 3d, like why do electrons fill 4s before 3d? It's a simple answer. You can answer it by saying as 4s has a lower energy than 3d. That's fixed. But how do we memorize the order? It's not going to be. It would not be possible that you would remember that 4s के बाद it is going to be 3d, then 3d, after 3d it would be 4p, and after 4p it would be 5s. How to remember that? There is a shortcut method. Let me show you how that works. One S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 4F, 5S, 5P, 5D, 5F, 6S, 6P, 6D, 6F. So that's what we know. Like the first shell have only one orbital, subshell 2, the second has 2, third has 3, from fourth they all have 4 subshells. Now how to memorize the order? Diagonal lines going downwards. First is 1S. Second is 2S. Then 2P and then 3S. Then 3P and then 4S. That's what I was telling you. 3P, then 4S. This diagonal line tells us about the order. Then 3D, then 4P, then 5S. Then 4D, then 5P, then 6S. Then F, D, P, and then 7S. That's the order, but we would never reach till 7th or 6th mostly. We're done with 3rd or 4th actually. So that is what we know about the electronic configuration and its order. So look at this. If we were talking about calcium, let's compare these. 1s2, 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3s2, 3p6, 3p6, then 4s. After 4s, we have the turn for 3d. It is after 4s we jump towards 3d. We have the next element after calcium, that's scandium. Sc21. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then after 4s2 we have one more electron left. If you count, these are 20. We have 21. 3d1. And after that, it starts making d subshell, which is a 5-block subshell, 5 orbitals. You will see somewhat like this. Let me show you what are we going to see here. For the d orbital here, students, this is what we get. Now that is the d elements. They all end with d. They all end with d. So 3d1, 3d2, 3d3, but 3d5 for chromium and 4s1. Why is that happening? Likewise, if we go down, 4s2, 3d5, 4s2, 3d6, 3d7, 3d8, 4s1, 3d10, 4s1, 3d10, then 4s2, 3d10. What is happening here? Why do we have S1 here and S1 here? What is the idea behind it? There are 2 ideas. One, remember, here we talked about that this is a half-filled orbital. And obviously we know fully filled is stable. Now we have 3 different types of orbitals. Either they are completely filled or they are half filled or they are partially filled. We are talking about P right now, but obviously D has the same idea. These are partially filled half, and full. Fully filled is obviously highly stable, that we know about. Half filled is somewhat stable. We want both of these. We never want a partially filled orbital. We don't want that. We don't want a partially filled subshell because it's unstable. It's highly unstable. So, what happens in the case of chromium? Cr24. 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d4. इसको हम कहते हैं, this is called ground state. Let me tell you why. If we look at the electronic structure, there is a chance that electron from a lower energy can go to higher energy and high can go to a lower energy orbital. And we've discussed in the previous lecture that is called excitation and de-excitation. Like if electron from a lower energy goes to the higher energy, that is excitation. And this is de-excitation. So if electron gains energy, it jumps from a low energy orbital to a high energy orbital. That is excitation. So what is happening here, students? Let me show you. Let's just draw these two, 4s2 and 3d4 orbitals. Ab isme, if we look at this is 4s2 and this is 3d4. Now, this is completely filled while this is partially filled. What is going to happen here? An electron will jump from here to here. This is excitation because it can happen. And this would give us 4s1, 3d5. One. Now it's stable. And we call it, the one here, 4s 3d1 as excited state. Likewise, in the case of copper, it was 4s2, 3d9. So one electron from 4s goes to 3d and that makes it 4s1, 3d10. This is the ground state and this is excited state. Same concept happening for both copper and chromium. These are commonly asked and you are supposed to make the excited state. Look at this. Half 4s completely 3d. We can't do it for other ones. Why? Because if I try to excite this electron from here to here for iron, it will make 4s half. We are at a loss of stability a little bit. But it will never make 3d full or half. So that's of no use. It is of no use. That is what we know about excitation and de-excitation and d orbitals. Now, the periodic table is divided on the basis of these. How come? When we look at the periodic table is now, it has different blocks. First two are S block, these 10 are D block, and these 6 are P block. And G lanthanide actinides are F block, but again not in syllabus at all. So let's ignore them. But why are these S block? Why are these D block? Why are these P block? What is the reason? lithium, beryllium, sodium, magnesium, even hydrogen. What is common in these? Even helium is also an S block one. What makes them S block? Let's look at these. Helium, S block, because the outermost subshell is S. S block. S block. Lithium, beryllium, S block. After boron, carbon, nitrogen, when we talk about boron, carbon, nitrogen, they are P block. Why? Because in that case, the outermost is P, 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 P. And the moment we jump back to sodium and magnesium, they are S block because their outer elements are in the S subshell. And transition elements are D block because their outer electrons are in D subshell. So on that basis, periodic table is divided in S, P and D, F block elements. On the basis of blocks are on the basis of valence subshell, like the outermost subshell that they have. उसी के basis पे we name them. अब हमने, what did we do? Like, I have a question. Why did we not, like we are saying for iron, we can transfer one electron. But can we transfer electrons from 3p as well to make it stable? The answer is no. Why? Because यहाँ पे लग जाता है एक block. We lock these. Why do we lock these? Why are we locking these all electrons inside? Because A, lower shell. These are a part of lower shell. But most importantly, these all have, इससे पीछे they are all 3p6. Where did we see 3p6? We saw 3p6 for argon. So noble gases, once we reach the noble gas configuration, we cannot remove further electrons. So इसीलिए, what do we do? अब हमें ये पता है कि we cannot use the inner electrons, we can only use the outer electrons. So what do? We use noble gases as checkpoints. मतलब, for instance, if I have to talk about silicon, silicon's configuration here was 1s2, 2s2, 2p6, 3s2, 3p2. It will go longer and longer. अब ये तो outermost है. I need to see them in my answer. But these are of no use to me. These are from the different shell. And they have the configuration of a noble gas. So what would I rather do? I would rather write neon in a square bracket and then 3s2, 3p6. So we use noble gases as checkpoints. Likewise, here, when we talk about calcium, this is the electronic configuration of argon. So calcium would be argon 4s2. Just use the noble gas. इसको देखो. Anyone, vanadium. Till here it's argon, right? So vanadium is argon 4s2 3d3. It is allowed. It is required. You take noble gases as checkpoints. देखो इसको कैसे करेंगे? If I have manganese, हमने देखा manganese से पिछली noble gas is argon. How many electrons are left? 1, 2, 3, 4, 5, 6, 7. दो तो S में आ गए. 4s2. 1, 2, 3, 4, 5. 5 are left. You can do that easily as well. या आपको पता है manganese has 25 electrons. इसमें से 18 तो argon के चले गए. बचे 7. 7 को divide कर दो. So that is how you can make a shorthand configuration that is required of you. That is what the examiner wants you to do. So students, that is all for today. In the next lecture, we are going to talk about the ionization energy, a very important concept and the most important concept of AS Chemistry chapter number 1. So thank you so much for being here with me. Take care and Allah Hafiz.